Okay, so let's go ahead and get started today. So the first thing before we get into the lecture, which is going to be on Carnot maps, I just wanted to let you know what I decided about next week. If there's a strike, and that's what I decided is that I'm going to be here, but I'm only going to lecture if half the class or more is here. If I come in and there's only like 3 people or something less than half, then I'm just going to have an open lab. Okay. And there's no penalty for not being here. So if you want to stay away from campus and, support the strike, that's your decision and that's fine. I'm not going to penalize anyone for not being here. Okay. But I will be here, like I said, and, if it's a half a class or more, I'll lecture. Now, if it is half a class or more and I lecture and you're not here, I'm recording my lecture so you can watch the recording at a later time. Okay. But like I said, if it's less than half, then I'm just going to have an open lab. Okay. All right. So Carnot maps. Carnot maps are a technique to reduce Boolean expressions. And last week, I gave you this handout that had 3 of the basic gates along with their truth tables. And then it had a whole bunch of the Boolean theorems and axioms. And you could use the information on this sheet and you could reduce a Boolean expression in a similar manner as you manually reduce a base 10 equation, okay? But Carnot maps is another technique. It's a pictorial type of technique that you can use to also reduce Boolean expressions. And past students have told me they actually kind of like Carnot maps, that even though they look a little strange at first, that once you kind of get the hang of it, it's almost like solving crossword puzzles. So, some people actually enjoy Carnot maps. So I figure out of the 2 approaches, since this one's a little funner, it's the one I cover. Now, when you're out in industry, you're not going to use these manual techniques to reduce Boolean expressions. There's programs, there's algorithms that you can use. But like anything else, there's, it's always good to have more than, one technique to do the same thing. And if nothing else, you can use a technique like this to, check algorithms. Okay. So here's the topics of the day. Like I said, we're going to talk about Carnot maps, and these are some of the subtopics of Carnot maps. And I'm going to do a bunch of examples here in class, and then I have an activity for you to do. Okay, remember, every class I have has an in-class activity where you can practice what you hopefully just learned about during the lecture. And then lab 1, which is the second lab of the quarter, lab 1 also involves reducing Boolean expressions. So, what you learn in class and what you practice on the activity, you'll also need for lab 1. And I'll talk a little bit about lab 1 at the end of the lecture today before I give you the activity. Okay. Oh, and remember that lab 0, the first lab, that's due tomorrow. So when we start into the lab portion of the course or the day at the end of the 3 hours, that's what you should work on first if you haven't completed that yet. Okay, lab 1's not going to be due until the end of next week. Okay. All right. So Carnot maps. Here in this class, we just cover. Here in this class, we just cover. Hold on a second. I don't want to lock anyone out like I did last week. Let's put this stuff here. All right, so in this class, there's 2 types of Carnot maps that we cover: an 8-cell and a 16-cell. The 8-cell comes from a truth table where you have 3 input variables, and the 16-cell is for when you have a truth table that has 4 input variables. Okay, and when someone looks at a Carnot map for the first time, there's a few things that kind of stand out that are kind of strange, if you will. And one of those things is that when you look at the numbering of these squares that are called cells. Okay, look at the numbering here. In this top row, it goes 0, 1, 3, 2. All right, then the next row goes 4, 5, 7, 6. And then if you look at the 16 cell, you got the same numbering in the first two rows. And then the third row, it jumps to 12, 13, 15, 14. And then it goes back to 8, 9, 11, 10. So, you know, when you first look at a Karma map like this, the first thing people usually wonder about is why is it numbered that way? Why is it in order? Like, why isn't it 0, 1, 2, 3, 4, 5, 6, 7? You know, why are these cells numbered the way they are? Well, they're numbered this way because when you number the cells like this, you get a property that's called unit distance. And unit distance just means that if you take any cell and you look at a cell above it or below it or to each side of it, there's only a 1-bit difference. So, for example, if we were to look at this cell 1 here, okay, so we're looking at this cell 1, which corresponds to this input combination in the truth table. Well, if you compare a binary 1 to 0, this cell that's right to the left of it, well, look, there's only a 1-bit difference between those two. And if you were to compare 1 with 3, right? So here's 1 and you compare it to 3, again, there's only a 1-bit difference between those two. And likewise, between cell 1 and 5, right? 1 and 5, there's also just a 1-bit difference. And that's true. You take any cell and you look to either side of it or above it or below it. And that is also true for the 16 cell. You'll have that unit distance property. And that unit distance property is necessary in order for this technique that I'm about to show you to work. Okay. You know, if this top row had been numbered 0, 1, 2, 3, and then you compared 1 to 2, right? You compare binary 1 to binary 2. See, that's not unit distance because there would be a 2-bit difference. Okay, so that's the reason for the funny numbering. It gives this property of what's called unit distance. Okay? Okay, the other thing that stands out is, you know, why is there an A here, you know, in front of this row? You know, why is this horizontal line here with a B? Okay? You know, why is there a horizontal line here with a C? And then down here, why is the A there? You know, why is the B? Why is the C? Why is the D? Well, the reason for that is if you look at this row A and you look at these indexes, 4, 5, 6, and 7 in your truth table, 4, 5, 6, and 7, well, A is equal to 1 for all those indexes, all those binary numbers. Okay, likewise, this row, this top row would be not A, because if you look at what A equals for 0, 1, 2, 3, well, A is equal to 0. And remember last week we talked about, when we were talking about getting an equation from a truth table, that wherever there was a 1 for a variable, we just called it that variable. But if there was a 0 for a variable, it'd be not that variable, right? Because if it's 0, it's not 1. Okay? You know, here, B, the reason why you see B here is because for these two columns, these indexes, 2, 3, 6, and 7, right? 2, 3, 6, and 7, see, B is equal to 1 for those binary numbers. Likewise, for this, or these two columns, we would have not B, because for 0, 1, 4, and 5, right? So 0, 1, 4, and 5, the B is equal to 0. Okay, and then C, which is the least significant bit, right? Remember, least significant bit furthest to the right? Well, if C is 1, that means you're going to have an odd index, right? So 1, 3, 5, 7, 1, 3, 5, 7, odd, C is equal to 1. So these two columns would be not C, right? Because those are the even indexes, right? Where C is 0. All right. So any questions on what unit distance means, or, you know, where these variables are coming from? Because it's the same idea with the 16 cell, right? Let's see these bottom two rows, A, because for all those indexes, 8 through 15, A is 1. All right, so these two rows would be not A. For these indexes, B is 1. So this would be not B. could also be not D. For these indexes, C is 1. So for these values, we have not C. And then here, D is the least significant bit. So these two columns have your odd values. And then the outer columns here would have the even values where we have not. Okay, does that all make sense? Now, what you put in the squares is what the output value is for that index, that input. So let's say, our F value, our output value for our truth table here with the 8 rows, let's say we had 1, 0, 0, 1, 1, 1, 0, 1, something like that. Well, for index 0, okay, so for this combination of inputs, right, everything 0, the output is a 1. So I put the output in that cell. For index 1, the output is 0. For index 2, the output is 0. For index 3, the output is 1. For index 4, output is 1. For index 5, output is 1. For index 6, output is 0. And for index 7, output is 1. So the output values go in the corresponding input block. Okay, and same thing for if we have a truth table with 16 rows. Each row corresponds to a cell in our table. So, again, this is like 1, 0, 1, 0, 1, and so on. We would just put in those output values into the appropriate cell. Here, 0, 1, and 1, and you would just fill in the 1s and 0s. Okay? All right, so any questions up to this point? This is just some basic information. Hopefully, like I said, when you first look at these, it looks kind of strange, but hopefully it's making a little bit more sense. Now we're going to get into, what the goal of all this is and how we actually come up with reduced expressions using these K-maps. Okay? All right, so the goal when you're using this technique with the K-map is that you want the least number of largest grouping. Okay, as you're going to see through these examples, the least number of groupings gives you the least number of terms in your Boolean expression. And the larger the grouping is, the less the variables you have in a term. Okay, so remember, the goal is always to get the most reduced expression. So we want the least number of terms and we want the least number of variables within a term. Okay, and by doing this, that will lead to that goal. Okay, now the type of groupings that you can do are rectangular and square. Okay, you can't do like a diagonal grouping. You can't do like irregular shapes. Okay, only squares and rectangles are allowed. And you can group either 1s or 0s. Group either 1s or 0s. Okay, think back to a truth table like we did last week, or even the truth tables that I have up on the board there. When we write an SOP equation for where the 1s are, we're getting SOP for what? What if we write an expression, an SOP expression, and we are looking at the 0s in a truth table? That's going to be SOP for, say it again? Yeah, so if our output is, say, F, it would be not F, right? If we look at where the 0s are, and if we look at where the 1s are, it's not F, it's F. Okay. Same thing with a K-map is that if we group the 1s, we're going to get an expression, a reduced expression, SOP for F. And if we group 0s, it's going to be the reduced expression for not F. Okay, so it follows along the same idea as when you take an equation right from a truth table. It's just with the K-map, you're gonna get the reduced expression, right? Because in general, when you write an equation from a truth table, that's not the most reduced. Okay? All right, so when you group the ones or zeros, depending on what you're after, right? SOP for F or SOP for not F, you can only group in these numbers. You can have a single grouping, a group of 2, a group of 4, a group of 8, a group of 16. So it has to be a group of a whole number power of 2, right? You can't have a group of 3, you can't have a group of 6. You know, these are the only allowed grouping. Okay. Now, if you have an 8-cell K-map and you do a single grouping, you're going to get a 3-variable term. If it's a 16-cell and you have a 1 grouping, you're going to get a 4-variable term. If it's a 2 grouping with an 8-cell, you're going to get a 2-variable term. If it's 16-cell, you're going to get a 3. A 4 grouping with an 8-cell is going to give you a 1-variable term. With a 16-cell, it's going to give you a 2-variable term. Now, if you have an 8-cell and all the outputs are 1, well, that just means your output equals 1 all the time, right? So it would just equal 1 if you're, got all 1s. And if you had a case where all the outputs were 0, well, your output would just be 0. Now, if you get a 16-cell and you have an 8 grouping, you would get a 1-variable term. Okay, 16 grouping in an 8-cell is not possible, so that would just be an NA. And then with the 16-cell, if all your outputs are either 1 or 0, well, that's what your output equals. So again, it would either be equal to 1 or equal to 0. Okay. All right, so now I've got a bunch of examples to go through, but before I start any of the examples, are there any questions up to this point? Again, this is sort of like preliminary information before we actually put this technique to use. You have a question? Well, any K-map you can do either. You know, any K-map usually has some 1s and 0s, and depending on what you're after, if you're after the most reduced SOP for F, you would circle the 1s. If you're after the most reduced SOP for not F, you would circle the 0s. And based on what we talked about last week, can you think of a reason why we might want to circle 0s and get the most reduced SOP for not F? Right, because then we can use De Morgan's twice to get the POS for F. Okay, so, again, the only difference is with a truth table, in general, you're getting a non-reduced expression. Using a K-map, you'll get the most reduced POS after you do the De Morgan's twice. Okay, does that make sense? Okay, so any other questions before we start these examples? All right, so these examples, I didn't choose like haphazardly, I didn't choose them just randomly for busy work. I chose them because each one brings up something that's kind of peculiar, okay? Well, the first one's kind of standard, but the rest of them bring up something, that I want to show, okay? But let's start with this as the first one right here, and let's group 1s. Okay, so we want to group 1s. Right? So remember, we're after the least number of largest groupings. So anytime you're doing a K-map, you always want to think, okay, if it's an 8-cell, well, can I group 8? Well, unless you have all 1s or all 0s, you can't group 8. But then, okay, can I group 4s? Do I have a group of 4 somewhere that, again, can only be rectangular or square, right? You can't have diagonals, you can't have irregular shapes. And you just kind of go down the line, you look for the largest groupings and just work your way down. So looking at this K-map, and we're after 1s, okay, because we want to get the most reduced expression for F here, SOP. So what would you do first? What would you group?
The left row, the 2.
Yeah, group these 2, right? We have a group of 2 here. Okay, and with a group of 2 with an 8-cell, that's going to give us a 2-variable term. And the way that you determine the 2 variables is you look at this grouping and you see what variables are common to that grouping. So looking at this grouping here, what variables are the same for this two grouping?
One, wait, oh, sorry, not C.
Okay, not C is one of them, right? Because both of them are in a not C column
Oh, not B.
and not B, because both of them are in a not B column. So you see, this grouping here would give us not B, not C. See, A drops out because in this two grouping, A changes, right? Because this one of this grouping is in the A row, and this one in this grouping is in the not A row. So if the variable changes, that's the one that drops out. Okay, you keep the variables that are common to that grouping. Does everybody see how I got not B, not C from this? All right, well, what would we do next? Because we still got this one over here.
Would it just be that one?
Yeah, it's just a single grouping, right? We don't have any other one nearby to group it with. So this is just a single grouping. So it's just gonna be that index. Right? It's just gonna be not A, B, C, right? We're just writing a 3 as a Boolean term. All right, so you see that would be our reduced SOP for F. Okay, so any questions on that example? Okay, ready for the next one? Okay, this one here, let's also group ones. Now, the reason I chose this example is because with K-maps, these edges touch. So it's as though this K-map was a cylinder and, we slid it and then we laid it out flat. Okay, so you can group through these edges. Okay, so knowing that, how would you group the ones here that the edges touch?
Do a 4.
Yeah, we have a group of 4. See, we have a group like this. Okay, and then what term would this give us? What's common to this 4 grouping? Just not C. Right, so see a 4 grouping with an 8 cell gives you a 1-term variable. So this would be not C. And because see with this 4 grouping, A changes, right? Because there's A and not A, right? These two are in the A row, these two ones are in the not A row. And then also B is changing, right? Because these two ones are in the B column, these two ones are in the not B column, right? So whatever variables change within that grouping, those are the variables that drop out. Okay? So any questions on this one? All right, let's go to the next one. Okay, again, we're grouping ones. So what would you do first? What would you group first?
4 in the middle.
Yeah, these 4 in the middle. Get an SOP for F. So what term are we gonna get by doing those 4?
C.
Just C. Right, just C is common to that 4 grouping. Okay, now, we got this additional one here in cell 6. And the reason I show you this example is because when you're doing K-maps, you can overlap groups. Okay, groups can overlap. So knowing that you can overlap groups, how would you group that one that's in cell 6? Say that again? 2 grouping, yeah. Yeah, we do this. Right, because again, you gotta remember, you want large groupings, right? Because the larger the grouping is, the less variables I have in that term. See, if I only circle the 1, that's gonna give me a 3 variable term. But by including this one, right, by overlapping and making this a 2 grouping, well, now I'm gonna get a term that just has 2 variables. And what are those 2 variables gonna be? Gonna be what's common here, A and B, right? Everybody agree with that, right? These 2 ones are they're both in the A row and they're both in the B column. All right, so any questions on that one? All right, well now let's group zeros. Okay, for this one here, let's group zeros. Like I said, you can use a K-map to either group 1s or zeros. It just depends what you're after, right? Am I after SOP for F, most reduced expression for SOP for F? Or do I want to get most reduced SOP for not F, therefore I can then use the Morgan's twice to get, most reduced POF. So, here perhaps we're after the most reduced, POF, so that's when we want most reduced SOP for not F. So how would you, circle these zeros? Could you do this? Could you do something like this, like do these four? No, why not? Yeah, it's gonna be a square rectangle, that would be irregular, right?
0, 2, 0.
Okay, so let's 0, 2. Okay, so 0, 2. What term does that give us? Not A, not C, everybody agree with that? Because B changes, right? B over here, not B over here, so it's not A, C. For that grouping. Or not A, not C, right? Not A, not C. Right, but not A is common, not C. That's what you said, right? No, not C. I just forgot the not for the C. Okay, what other grouping did you say?
0, 1.
Okay, 0 and 1, because you can overlap. That's 0 and 1. So what grouping would that give us?
Then not B.
Not A, not B? B, all right, and then what would you do next?
5 and 6.
5 and 7. Okay, so 5 and 7, what is that gonna give us?
Yeah, it's
8B. Okay, so for the groupings that you see here, we would have not F equal to not A, not C, or not A, not B, or AC. Now, if my intention was to now, after getting most reduced SOP for not F, to now get most reduced POS for F, what would I do? Like, how do I take this SOP for not F and make it POS for F? Remember from last week, what did we do?
I switched the maps to not, and then just change the multiplication button. I don't really know how to think better than that.
Yeah, no, you said it right, that we would invert all the variables, change ands to ors. Now, you said multiplication, we think of and like logical multiplication, but yeah. And so ands would go to ors, and then these ors would go to ands, right? So, for example, over here, up here, make it up here, we would write it as F. And then this would become A or C. And then that's ANDed with A or B. And then that's ANDed with not A or not C. Right? Because we invert everything and we change ands to ors and ors to ands, right? And again, you saw the derivation of that last week, right? You do De Morgan's twice. Okay, but now that you've seen the derivation, you could just do the end result. Oh, now, a reason I picked this one is because can anyone see that we could group these zeros slightly differently and have the same, have a different but the same reduction, like another most reduced SOP for not F, but it would be a slightly different equation?
Do 1 and 5.
Yeah, exactly. If we did 1 and 5 instead of the 0 and 1, we would still have, let's see, we would still have the AC term, the not A, not C term, right? Because that came from 0, 2. And we would still have the 5, 7 term, which is the AC term. But now if we group the 1 and the 5, what would the 1 and the 5 give us? Not BC? Not BC. So, we could write, instead of this, we could also have not F equals not A, not C, or not BC, or AC. So I show you this example just to, give you a case where the same K-map can give you, more than one correct solution, right? You can sometimes get more than one most reduced equation from a K-map. Okay? All right, so any questions up to this point? Because we're gonna get a little crazy with the next one, because look, in this K-map, there's something you haven't seen before in this class, and that's a dash. But before I tell you about the dash and you do that, is everybody okay up to this point?
You're right, Megan, why, like for the last one you said. How come we didn't make rectangle notes 3 wide this year, instead we did 2 that overlapped?
Yeah, it's because the number of the groupings that you're allowed has to be a whole number power of 2. Yeah, it just doesn't work for any other number of groupings. So yeah, it's either gonna be 1, 2, 4, 8, or 16. It can't be any other number.
Okay.
Any other questions? All right, so let's do this, well, let me turn the camera on, so. Forget. Here. Okay. So yeah, let's look at this. So we have this dash. What the dash means in this case is it means don't care, doesn't matter, irrelevant. Okay, however you want to say it. So what we mean in this case by a don't care is that output, because remember, what goes inside the cells are outputs. That output can either be a 0 or 1. Okay, we don't care. It's got to be one of the two, but it could be either. And the most common example of a don't care output is when you have an output that's not connected to anything. Okay, I mean, there are some cases where you have a device and maybe it has multiple outputs and you're not using all the outputs, right? There's nothing that says that you have to use every output of any particular device. So since it's a don't care, we can make it either a 0 or 1. It's sort of like a wild bid, if you will, kind of like a wild card that will make a don't care equal to whatever's going to lead to the least number of largest groupings, because that's going to lead to the most reduced expression. Okay, so looking at this example here, and let's say we're going to group 1. Okay, so we're back to grouping 1. If we're grouping 1s, what would you make those don't cares equal to? You want to make both of them 1? Like you want this?
I would make 6.
You would make 6, 0. Okay, how many people? So it sounds like we have agreement between you two that this should be 1. Okay, but we have a little bit of a disagreement here, maybe?
Well, do they both have to be the same or?
No, they can be different. Say that again?
I do.
Oh, okay, so you changed your answer. So you make this a 0? Is there anyone that would do something differently? So how many people agree 1 and 0 like we have it on the board? How many people say there should be something different? How many people don't like raising their hands? Ah, caught you. Why'd you raise your hand? Yeah, this is right, because see, just think, if we didn't make this a 1, right? If we made this a 0, how would I group these 1s here? Yeah, you have 2 groups of 2, right? So that's 2 terms that have 2 variables. But by making this a 1, I only have 1 grouping, which is 1 term, and that term is only 1 variable. So what's more reduced, 1 term, 1 variable, or 2 terms, 2 variables? Obviously, it's the 1 term, 1 variable, right? So that's why you always have to keep in mind what the goal is. Okay, and then clearly, you don't want this to be a 1, because if you made this a 1, what is that going to do? Yeah, you just have you could group it over here. So you'd have another grouping of 2, right? So that would have a whole nother 2 variable term. So yeah, you guys are right that that should be a 0. So what would you then do? Yeah, just this one group of 4. That's what we would have. So this would just be equal to What's common to this four grouping? Not B, yeah. Okay, so everybody good with that one? All right, let's see, this next one, let's see, what did I group for this next one? Oh, the next one is grouping zeros. Okay, so this one right here, we want to group zeros. So what would you make the don't care is equal to? Does everybody agree with that? Make them all equal to one? Yeah, because if we make them all equal to one, we just got a single two grouping. Right, if we made any of those don't cares at zero, we would be adding to our expression. Okay, see, the reason I chose this example is just because, you know, a lot of times I think people think that, you know, they have to make the don't care equal to what they're circling, you know? But it's okay to make the don't care equal to what you're not circling. Whatever leads to the most reduced, that's what you're after. So this would just be F equal to. Not A. Everybody agree with that? Common to the not A row and the not C column. Oh, what did I forget here? I made a mistake. What mistake did I make right here? Because we're circling zeros. Yeah, it's not F. All right, so those are all the 8-cell examples I have. I now have some 16-cell examples, and really the only difference with the 16-cell is that, you know, when you have a grouping of 1, it's a 4-variable term, grouping of 2, 3-variable, grouping of 4, 2-variable, grouping of 8 would be a 1-variable term. But really the concept is the same. Another difference is, you know, with an 8-cell, you just got to worry about, you know, these edges touch. With a 16-cell, not only do these edges touch, but these edges touch. So the 16-cell, it's sort of like a sphere that you split and lay out flat, like, you know, a flat map of the earth, if you will. Okay. All right, so let's do this first 16-cell, and let's say we're going to group ones. So we're looking at this K map here, and we want to group one. So where would you start? Now again, the edges touch. Just 4 and 12? Oh, all right, yeah, 4, 12 and the 6, 14, right? Because yeah, we can do a 4 grouping like this. Okay, so that's going to give us, let's see, what term is that going to give us? Now, when it's a 4 grouping in a 16-cell, it gives us a 2-variable term. So there's 2 variables that are common to this 4 grouping. What are they? B, is it not, did you say not what? B. Is it not C? It's B, yeah, B not D. See, they're both in the B row and then the D column. See, this is not D down. Yeah, the not C would be changing, right? Because these 2 ones are in the C column, these 2 ones are in the not C. So, yeah, that would drop out. So it would be B, not D. Okay, what would you do next? Yeah, 4 and 5, we have a 2 grouping here. Okay, and that's going to give us a 3-variable term. Let's see, what 3 variables are common to this 2 grouping? Not A, not B, C, is that what you said?
Yeah.
Right, does everybody agree? The not A row, not, let's see, it's not A row, and then it's not B. Did you say B or not B? Oh, okay. I'm sorry, I misheard. And then not C. Okay, sorry, that was my mistake. So yeah, B and then the not C, right? D changes, right? Because this is in the D column, this is in the not D, the D drops out. Okay, what do we do here with this one? Yeah, we can't group it with anything else, so that's just a single grouping. So that's just gonna be, you know, that index in as a Boolean term, so it's just gonna be not A, not B, C, D. Right, you're just writing 3 as a Boolean term. Okay, so any questions on this one? Let's see, we got 3 more to go. We'll do ones here, and then we'll finish with zeros here. All right, so let's do this one here. We're grouping ones.
Or in the middle.
What for? Okay, do you want to do this grouping here? 5, 7, 13, and 15. All right, so this 4 grouping, what is it going to give us? What's common to these 4? D and B. Yeah, another thing, and this is just purely for ease of grading because it doesn't matter the order that you put the variables in, you know, BD is the same as DB, but you know, if you could, I would appreciate if you put them in alphabetical order. It just makes it easier to grade. You know, if you don't, I'm not gonna take anything off, but you know, it'd be nice, you'd make me happy if you put it in alphabetical order. Just makes it easier for an old guy like me. Okay, what else, would you do here? So you said 13, this here? Do you want to do this right here? No, it can be rectangle. It's either rectangular or square. So if you wanted to do this row, you can. Like that would be, right, because that'd be rectangle. So yeah, that's good. You can do that. So what term would we get for this row? AB, right? AB. All right, so what would you do next? We still got these 2 ones down here. Yeah, do 4 like this, because remember, you can overlap. That's probably one of the most common errors that's made is that people don't overlap when they can. Okay, so remember, you can overlap groups. Okay, so what term is these 4 going to give us? AD? All right, the next one brings up something peculiar. Okay, but what right away should stand out as a grouping that you can do? Because in fact, we did it earlier. Well, we're gonna get to the corners in a minute, but what other grouping? Yeah, right in the middle again, just like up here. Or no, I guess we did a middle grouping. Yeah, so yeah, this here, that's just like what we had here, right? It's gonna give us BD. Okay, but the peculiar thing here, and the reason I have this example is you can group corners, right? And this goes to, remember that this 16 cell K-map, it's like a flat map of the earth that, you know, since these edges touch and then these edges touch, it's like a sphere. So, you know, the corners are like a pole of that sphere. Okay, so when you have corners of the same value, like we have the 4 ones in the corners here, that makes a 4 grouping.
Can you group 2 opposite corners?
No, you can't, because that would be diagonal. And that's a great question because that brings up the unit distance again. See, if you try to group like 0 and 10, and you look at 0 in binary and 10 in binary, there's not unit distance between those cells, right? Because, you know, if you have 0, everything's 0. If you have 10, you have 1, 0, 1, 0. So there's a 2-bit difference. But yeah, that's why you can't do diagonal groups because it doesn't have that unit distance property. But yeah, that's a great question. Okay, so what term would the 4 corners give us? Right, exactly, right? Because the 4 corners, they have not B in common and they have not D in common. So this is unique. Okay. All right, we're at the last one, at least the last one that we're doing at the board. Like I said, I have an activity that's got more examples for you to practice, but this is the last one we'll do at the board, unless you want to do more. I'm open to, suggestions if you want to see any other, example here, but let's do this one here. We're after zero, so this is gonna be not F. And we got some don't cares. Okay, so we're grouping zeros. So first of all, what would you do with the don't cares? Like, what value would you make the don't cares? One. Yeah, does everybody agree, make them one? Yeah, making either of those don't care zero is just gonna add to the equation. Okay, so how would you group the zeros that we have? Okay, yeah, so these four. And then how would you group this? Yeah, that's it, right? So we got one grouping of four and one grouping of two. So looking at the grouping of four, what term is that gonna give us? What's common?
Not C, not B.
Not C, not D, yeah. And then this two grouping is gonna give us what? It's gonna be a three variable term. So what three variables? A, not B, not B. Yep, the two groupings in the A row, the not B row, and yeah, the not B column, yeah. So everybody agree with that? It's good? Okay, so hopefully, these K-maps don't look quite as strange as maybe they did when you first came in. I have an activity for you to do that I'll pass out in just a second, but before I pass that activity out, I just want to go over lab one, okay? Now remember, like I said at the beginning of class, lab zero is due tomorrow, so if you're still working on lab zero, that would be a priority when you get to the lab portion of the day. Okay, but for those of you that have finished lab zero, when you finish the activity, when you pass it in, you would want to work on lab one. Give the projector a minute to warm up here. It's coming. Okay. So this is lab one. Lab one, you have a lockbox. And it's got a 4-bit input. And only these combinations, I think there's 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 of the 16 combinations, because 4 input bits, so that means we have a truth table of 16 rows, like we talked about earlier. And when you have these 9 combinations, input combinations, that will unlock the lockbox, and that's represented by the output being a 1. Okay, so what we want you to do first is, draw the truth table, and then from that truth table, come up with the unreduced SOP and POS, right? So this is what you did last week, right? Because you didn't know about K-maps until today. So the first thing you do, draw the truth table, and then just like last week, just write the SOP and POS equations for F, right from the truth table. Okay, your non-reduced SOP and POS. Okay, we also want you to draw the black box diagram. Okay, remember last week we talked about this? What does the black box diagram show us? What did it show from lab 0? And it shows it for every black box. Yeah, it just shows your inputs and outputs. So, lab 0, you had 3 inputs and just 1 output. And I guess I don't remember what we called it. Maybe it was just Q. Okay. Well, here, how many inputs do we have? 4. A, B, B. And then you're gonna have an output for each form of the equation. So you're gonna have an output for SOP and an output for POS. So in lab 0, you just wrote one Boolean expression, right? That same one that I showed you in that video that, showed you how to get started in Bravado. Well, in lab 1, you're gonna have two equations. So that means in your design source, you're gonna have two assigned statements. Okay, one SOP, one POS. Now, in addition to having the non-reduced expressions, we also want you to use K-map to get the reduced SOP and the reduced POS, right? So that's when you use the technique that we just went over today and what you'll be using in the activity. So the equations that we want you to use and write in Verilog is we want you to write the reduced expression. Yeah, and then, that's the last part of it is to build, build those two reduced expressions in Vivado. Now, this isn't the entire lab 1. This, as you can see, this is part 1, but this is all you can do up to this point. Next week, or the next time we have lecture, we're gonna go over two other forms of logic circuits, NAND, NAND, and NOR, NOR. And once you know about a NOR, NOR, you're gonna add a third output. And the key thing that we're trying to get across in this lab is that these expressions, SOP, POS, that you've learned thus far, and then also NAND, NAND, and NOR, NOR that you'll learn next week, they're all logically equivalent. So when you simulate in Vivado, when you simulate the truth table for any of these three forms, you're gonna get the same output, or you should. And when you demo it on the Basis 3 board, you should get the same output. You're gonna have, you only had one LED for lab 0 because there's only one output. For lab 1, you're gonna have 3 LEDs, right? You'll have an LED for SOP, LED for POS, LED for NOR, NOR. And if your design is working the way it should, those LEDs are gonna be in sync. They're gonna give you the same truth table. Okay? As we talked about last week, the advantage of having these different logic forms is that, depending on the particular problem you have, it's likely that one of these forms is going to give you a more reduced expression that has less gates that does the same thing, right? And if you got 3 different circuits and they do the same thing, give you the same truth table, and one of them has 4 gates and the other one has, 15 gates, and the third one has, 12 gates, whatever it may be, well, why not do it with 4 gates, right? Because it gives you the same thing. Okay, so do you have any questions at all? Like I said, I'm going to hand out the activity. That's the next thing to do. And then, like all my activities, I have my answers up there so you can compare them to mine once you're done. And then you're ready to either finish lab 0 or start on lab 1. Okay, question? Well, first of all, hopefully the strike will be solved before then. And personally, no, I'm not like Nostradamus or anything, but personally, I don't think it's gonna go the whole week. I mean, I can't imagine, the optics is gonna look really bad, especially the campuses like down south and up north, I would think, where there's more probably media coverage. So I would doubt it goes the whole week, but I don't know, maybe it does go the whole week. I don't, who knows, but we'll cross that bridge when it comes to it. And like I said, as far as I'm concerned, I'm gonna be here. One of the reasons I chose to do that is, you pay ridiculous amounts of tuition and, I personally think that one of the demands that the union should have is that students should be reimbursed any time they miss. Like if you miss a week, that's 10%. Like you're paying 10% of your tuition for no classes. That's not fair. And they say, oh, well, call your representative, but politicians don't listen to young people because young people as a whole don't vote, right? Their jobs don't depend on young people. I mean, if young people voted, I think this country would be in a lot better shape. To tell you the truth, because old people have really screwed it up, including myself. Okay, but that's just my personal opinion. And like I said, if you choose not to come, I'll be here, but if you choose not to come, I respect your decision, and, that's why I say I'm not gonna penalize anyone for not being here. It's up to you. Okay, well, let me, pass out the activity and you get started on that. Oh, yeah. I'll talk about that in just a second. You get to know that. Oh, yeah, I'll get you in a minute. Yeah, so the question that Sean had was about the symbology, and I talked about this last week, but it was, it was rather fast, so I can understand that you might not remember. And that's the sigma sign and the capital pi sign. That's that compact min and compact max notation that I talked about. It was pretty quick last week. So if you see the sigma, the numbers within the parentheses to the right of the sigma, that's telling you the indexes, the squares, where the output is equal to 1, right? So for that top left, for cells 1, 3, 4, and 6, you'd put a 1 and all the other cells would be 0. And then if it's a capital pi, that's telling you the inputs where the zeros are. Okay, now, for all 8, I want you to come up with the most reduced SOP for F. And then just for the 4 K-maps on the right, I also want you to circle zeros and get the most reduced POS for F, right? So circling the zeros will give you the most reduced SOP for not F. And then remember De Morgan's twice, you then go to POS for F. Did you have a question, Joshua?
Yeah, just the like diagonal line at the top with the.
Oh, it's
saying.
Yeah, it's just saying like A, B are on the horizontal and C is on the vertical. But no matter how the K-map is drawn, no matter how it's oriented.
Oh, I see.
Yeah.
Okay.
It's just kind of like it turned it, but this is what's always true. What we talked about here, that, the A row, or if it's an A column, 4, 5, 6, and 7 have to be,
Yeah.
in that row. Right?
Okay.
Okay, so any other questions before you get started? And remember, with these in-class exercises, you can work together, help each other out, ask me questions, and then, compare your answers to mine. And then remember also the last hour from 5 to 6, my ISA Kathy will be here to help out with the lab section. So she'll be here.